Acorda, Maria Bonita.
Okay. Hola. Lucas, everybody else? Ah. Okay, then we can start. ¿Y tenés el control? Sí, it's right. Estaban todos viniendo conmigo. Sí, ¿qué tenés? Creo que tenés 45, me parece. Sí. Tenías 45. Bueno, 50. Perfecto. Te aviso cuando faltan. Okay, let's start. So it is a pleasure to present my dear friend Paulo Natenzon from WashU, who's going to talk about random choice and differentiation.
Thank you so much, Leandro. It's a great pleasure to be back here. So many memories from the time I was a student, and so many mentors and peers in the audience. So thank you so much to the organizers for having me, and it's really a pleasure to be in this very distinguished lineup of fancy presentations. So I'm going to give you a talk about random choice and the role of differentiation for choice. And some of you have seen preliminary versions of this paper, and it has evolved quite a bit. And so I'm looking forward to continuing the conversation and getting more feedback until this thing is finally published. So this is joint work with my student, Junan. He's at Sciences Po. He's an amazing kid, and you'll see him do amazing things in the future. So here's the motivation. I'm going to tell you what I'm going to study and why it's important to study it. Okay. So the variable that I'm interested in is product differentiation. Okay. And so why is product differentiation important? So if you have had a class with the logit model, you know the logit model lacks something very important. The logit model doesn't allow for product differentiation, doesn't allow for any horizontal differentiation, and that leads to a series of problems. The main issue is, for example, in I/O, you want to capture the fact that some objects are more similar than others. Okay, so if you have two minivans, and you want to have a demand system, and you want to predict what will happen when you raise the price of one of the minivans. Let's say that we make this minivan more expensive. You know that some of the population, that this minivan is going to lose market share. Okay. So now, it's natural that the person that gives up on buying the first minivan because the minivan got a little too expensive for them is more likely to switch to another minivan than to switch to a coupe. Okay. And so, the logit model can't do that. If they start with the same market shares, then the model will say that the person who gives up on buying this minivan because of a price increase is equally likely to go to each one of these. So we need to account for the level of differentiation between the products if you want to properly specify the demand system and make predictions. Very related to that, in behavioral economics, when people are making mistakes, in psychology and even in biology, the level of differentiation of the options also affects something very important for us to fit and predict behavioral sample, which is the level of the easiness of comparison. So this is another experiment in psychology by Tversky, where prisoners were trying to guess which one of these rectangles has the largest area. Okay? So you saw a bunch of pairs of rectangles. You're trying to guess which one is the bigger one, which one has the largest area. And if you get it right, then Tversky will pay you with cigarettes, because in the 70s, the IRBs will allow you to pay the experimental subjects with cigarettes. So 85% of the subjects correctly identified this rectangle as being bigger than that one, okay? And these two rectangles have exactly the same area, so it was a 50-50. But you notice that the first rectangle and the third rectangle, only 67% of the subjects correctly identified the one on the left as being the bigger one, okay? So if, like in the logit model, you only have one variable, which is the size of the rectangles to explain this, you can't do it, because these two have exactly the same size, so they have the same utility. That means that the gap in value between each one of these on the right and the one on the left is the same. So you need something else to explain why is it that these two are easier to compare than these two. And again, you can think of this as some form of similarity or differentiation between the objects. You need a second dimension to say these two objects are more similar to each other and therefore easier to compare than these two. Okay. And it will turn out that the framework that I'm going to show you today and the representation theorem I'm going to show you today is going to allow me to have a variable that captures the level of differentiation of the options, which you can use to study and bring to data in things in psychology like this, when you're trying to explain the mistakes that the agents make in choices, and also to bring it to demand systems and do I/O, taking into account the level of differentiation of the options. Okay, so this is what I'm doing, and this is why it's important. And I'm going to give you now. I'm going to give you one slide to tell you what the data is like, or what's my primitive, and then I'm going to give you the main theorem straight away. So we're talking about probabilities of choice when individuals are making repeated choices, or when you have a population coming to the lab trying to guess the rectangles. Or you could be talking about the market shares. Okay, so what you have as a primitive is a random choice function. I'm going to call it rho of object x when the options are x, y, and z. Okay, and that is the probability that x is chosen from the menu of options x, y, and z. Or you can also interpret it as the market share of product x when these are the available products. Okay, and of course they have to add up to 1. In the special case of binary choices, when I'm doing binary comparisons in the lab, or when I only have a duopoly, I'm going to use the notation rho of x, comma y to be the probability that x is chosen when x and y are available. Okay. So this object here is my primitive, is what we're going to call the data that I get to work with. Good. So what do we do with this data? I'm interested in what are the conditions under which I can interpret data as being generated by this formula. So the representation theory we're going to have these objects are going to live in Rn, or in any finite dimensional vector space. And the probability that x is ranked over y in somebody's preference, or the probability that x is chosen over y in a direct comparison, is going to be represented by this formula here that has 3 parameters. So inside the brackets, I have a ratio. Okay, so x is going to be chosen over y more frequently. First, when the difference in utility between x and y is larger. Okay, so I'm going to be directly proportional to the difference in utility. There's going to be a utility function. I'm going to make it linear between x and y. But before I plug it into the f, I'm going to divide. I'm going to make this inversely proportional to an inner product norm. I'm going to have a notion of distance between the objects. It's going to be really, I'm in Rn, so I'm going to make it really nice. It's going to be a norm. The norm is going to be generated by an inner product. And that's my variable of interest. That's the level of the differentiation between x and y. And I'm going to show you in a second how it plays exactly the role that we want it to play. And that ratio, which you could interpret as some sort of strength of preference of x over y, gets plugged into a strictly increasing continuous function that transforms that ratio into choice probabilities. Okay. So my formula, the formula that I want you to, that we're going to discuss today, has 3 parameters. It has the f, strictly increasing and continuous. It has a linear utility function, and it has a distance notion, which is going to be an inner product norm, and we will represent the level of differentiation of the options that I'm interested in. Dewey.
And for menu with more than two?
Yes, excellent. So we're all interested in multinomial choice, and in fact, that's the main thing that referees have asked for, that people have asked of after companies. So I'm going to prove a representation theorem using binary choice, and then I'm going to use it in 3 applications using multinomial choice. Okay.
No, in particular, in the 2 examples that you started.
Yes. Yeah, I'll relate it to it in a sec. So the main theorem is going to say, look, my behavior can be represented by this formula if and only if it satisfies continuity, linearity, independence, and moderate transitivity. Okay, so there's going to be, the main theorem is going to say, look, this can be thought of as the data generation process if and only if the data that you see satisfies these 4 testable implications. Okay. So this is useful. Why? Because you know, when you wanted to measure differentiation or plug them into the system, you have some conditions to check directly on the data, or some assumptions like continuity that you have to make directly on the data in order to know, to have the foundations for why you'll be able to measure differentiation with the formula. Okay, this formula, first let me show you how this formula why the differentiation here in the denominator does exactly what we wanted in the motivating examples. Okay. So think of the case of the two minivans. I'm going to call M1 the first minivan. I'm going to call M2 the second minivan. And I'm going to call C the coupe. So look at what happens when we decrease the price of the first minivan. So I'm making an assumption here that when I decrease the price of the first minivan, I'm increasing the level of utility of the minivan without affecting the level of differentiation between the minivans. So this is the distance, the differentiation between the minivans, and in the numerator, I have the level of utility of the minivans, and I'm going to make a usual assumption that we make in I/O, that when you change prices, you're affecting this parameter, the differentiation in the numerator, but you are not affecting how differentiated the products are horizontally. Okay. So what happens is that the derivative of the probability of choosing the minivan over the first minivan over the other, the probability that somebody ranks the first minivan as above the second minivan is going to be the derivative of f with the ratio here, and then chain rule, you have to do 1 over the level of differentiation. Now, naturally, if I make the distance between the two minivans, naturally, if I differentiate it, so I make them closer to each other, then this number here in the denominator is going to be much smaller than the number between each minivan and the coupe. Okay. So this distance or differentiation is capturing the fact that these two minivans are more substitutable than each one versus the coupe. And so when you divide by something small, you get something bigger than when you divide by something big. And then you see why the impact, or the number of people that will switch over from one minivan to the other when you make it cheaper is going to be larger than the number of people that would switch from the coupe to the minivan. Okay, so this is exactly how this formula captures the fact that some things are more substitutable than the others. That's how you need that metric to do the job. Let's go do another one. For the rectangles, or in general, when you have an agent who's in your lab trying to maximize utility and sometimes making mistakes, you have a behavioral story. Okay. You could have, let's say that the objects are in some attribute space. So I'm put here just 2 dimensions. And you could say that, like, if the agent really had all the time and all the attention and all the cognitive resources to figure out the utility exactly, that she actually has a utility function. She has these 2, I just plotted 2 indifference curves. All the objects on the top indifference curve have utility U1, okay? And that's larger than the utility of all the objects 3, 4, and 5, and 6 underneath. Now, you would expect that if you put these 2 options, 1 and 4, against each other, there's dominance there. And it's much easier to compare these 2 than to compare, for example, number 1 and number 6. Right? So a logit model will not be able to capture that because you have one parameter for how good 1 is and one parameter for how good 4 and 6 are, and they have exactly the same utility. So the prediction of a logit model is that this choice problem is identical to the problem 1 and 6. And so our formula has a distance metric here that allows us to capture the fact that these 2 are closer to each other. So you put in the denominator, you put a tiny number, so you make the ratio be bigger, and so the probability of choosing 1 over 4 can be as close as, can be very big, while the probability of choosing 1 over 6 can be 60% or closer to 50%. So the level of differentiation between the options in this formula allows you to capture the fact that some problems are easier than others, even though the difference in true utility is exactly the same, because we're talking about the same gap between the 2 utility functions. Okay, so this is sort of to help you see what is the formula in motion. Where does the differentiation enter, and how exactly does it capture what we want to capture? Christoph.
No, I haven't woken up yet. So, but isn't there a kind of a tension between this example and the other example, and there's also the drift diffusion processes, that sometimes an easy problem is when the objects are very different. Then you can decide. When they're very similar, then you can. So like what's close and what's different seems, at least at some implicit level, different in these 2 examples.
So similar and different can confuse 2 things. I can make you similar continuously. I go closer and closer and closer, and eventually become you. As we do that, I am, on the one hand, having our distance in differentiation will go to 0, but at the same time, our difference in value will also go to 0. So when we just think of the pure similarity, one object becoming the other, we're confounding the two. This is why it's essential that we keep them separate. I'm saying, keep the gap in distance between us the same. You are going to be the better object than me. Okay, you're going to have more utility. And I'm going to go get closer to you, but I'm going to get closer to you on the same utility. So from 6, I'm going to go to 5, and then I'm going to go to 4. And once I get that close, the gap in value that existed all the time between us will become very, very obvious to see. It's just that, like, if I'm worse than you, I actually want to be more differentiated, so that, you know, maybe I appeal to customers over here and I have a higher chance of being picked. If I'm less and less differentiated, but I'm worse, I'm going to be obviously worse, and then nobody's going to pick me.
Very nice. So I'm wondering how this is, what it adds to the one-on-one thing that we learn in I/O when you have differentiated products on a line, and they have a distance between them, and so they're differentiated, but there's also have a price. So I guess it adds something, but the idea of distance is there already in some sense.
Fabulous. So this formula is a very general formulation. Like in I/O, we all had to solve the problem that the logit doesn't do the job, right? So we came up with a million solutions. You could say, like, look, I can do less than logit, I can do a covariance probe it, I can do elimination by aspects, and in psychology, I can use Coombs. I have something called the Bayesian probe it to explain behavior in the lab, and then some other recent papers. All of these, the idea is like, look, we came up with lots of solutions. What this paper is saying is like, all of these solutions are picking up specific functional forms for the distance and for the utility and for the F. So once we understand exactly what are all the consequences of this, we're actually doing it in a cleaner way. Just give me a metric distance, and we're going to get lessons for for a large variety of specific cases. People develop solutions, and sometimes they didn't realize they were doing a special kind of metric. Nested logit is something called a hypermetric, or like a specific metric that is a clunkier metric, but it's a metric. And so this is sort of a way of saying, let's say, a more elegant or general solution to a very general problem that's been solved in clunky ways a million times. That's my spiel. Yeah.
Let me make sure I'm getting this right. So I can understand this in two different ways. One is discernibility notion that has to do with perception. I can compare triangles better than I can compare triangles with circles. All right. Another way to think about it is horizontal differentiation a la hoteling. My preferences are location-based, because I want to go to a store near my house versus a store far away from my house. And people are differentiated based on where they live, and therefore they have different preferences based on location. You're saying I can hit both birds with these functional forms.
So when we look at binary comparisons, you can hit both birds with one stone, but they're going to have very different consequences when we go to multinomial choice. So the short answer is, I'm going to show you some characterizations of multinomial choice for the heterogeneous population of rational people, okay, I/O style. And then let's say the frog paper is an example that is completely different consequences. But when you look at those in binary choices, it's basically the same. I'm going to show you how to tease that variable that is important for both settings with very different consequences, but the math is going to be exactly the same for binary choices.
Fantastic. Let me do a follow-up question, though.
Yeah.
Suppose I'm sticking with hoteling. So you're capturing horizontal differentiation based on where we live. There seems to be, though, an implied distribution of taste based on distance.
Yes, I'm going to pin it down to elliptical distributions.
All right, I shut up.
Yes. No. That's awesome. You're doing my job for me. Thank you. Okay, so let's go. So that's the theorem. So what I'm going to tell you is, I'm going to tell you properties of the model. Okay, so why do we have the representation model? One, you have foundations. When is it okay to say I'm measuring the differentiation? But also, you need a uniqueness result. You need to know when is it that I can pin down the F, the U, and the D, and the distance, so that I can say that I'm actually measuring the level of product differentiation. So I'm going to tell you about the uniqueness properties of this formula, and then I'm going to tell you about those 4 axioms that fully characterize it. Okay, and then I'm going to briefly mention, once we have this theorem proved for just like a general finite dimensional space, that we can bring it to have some lessons about random coefficient models of demand in I/O. I can take it to the setting of Gould-Pessendorfer 2006 and talk about random expected utility. When can you measure differentiation in random expected utility? And finally, we can go back to a problem that's been open in the abstract finite random choice literature since the 50s and the 60s, which is what happens when I just have a finite collection of objects, and we'll see what happens there as well. Okay, so we're going to have those three applications, but first let me go through the main formula and the theorem. So this formulation where you have an F comes all the way from the 19th century in psychology. Okay, so Fechner had this formula without anything in the denominator. Okay, Fechner only had the F and the distance in utility. It's saying, look, my ability to discriminate between two things depends on the gap in value. Okay. And in the 70s, Henry Huff noticed that probit and elimination by aspects and others were a particular case of taking the Fechner formula and adding a distance right here, okay, in the denominator. So the idea of using the ratio between value and distance is already in this 3-page note in the Journal of Mathematical Psychology in the 70s. What we're going to do is, instead of doing it in a finite space, okay, where, you know, he just made this observation. He said, like, look, all of these models actually take this form, and then made some conjectures about what the characterizations could be like. What we're going to do is do it in a more useful scenario where I'm going to have attributes. Assume that I have a bunch of observable attributes, so I'm in a finite dimensional space. And then I'm going to make that utility that was abstract a linear utility, and I'm going to make the distance, which is just an abstract distance metric, I'm going to take advantage of this linear space and make it a really nice inner product norm. Okay. And you see that you can write it in this way, or if we wanted to do estimation, we can rewrite this formula. So here I have a linear utility, so you can think of this as the Bernoulli index. This is a vector, okay, that has your, for your linear function. And the inner product norm can always be written as this generalized Gaussian distance, okay? So it's like Gaussian distance, but you have this variance-covariance matrix in the middle, okay? So the inner product is determined by this matrix. This matrix has to be positive definite. And so you can think of the formula this way, or if you're going to estimate it, you can think of this as your variance-covariance matrix, this as your vector of utility, and then you also have to estimate the exact shape of the strictly increasing transformation F. Okay, so my model will have 3 parameters. You can think of F, U, and the capital sigma. Okay, so how unique are my F, my U, and my capital sigma? So obviously, one possible transformation I can do is that I can multiply, take the old utility function that was in the numerator and just scale it up by a constant b and make a new utility function. Then I can take the old distance in the denominator and scale it up by another constant, c. So I can play around with 2 strictly positive constants, scale those up, and then undo the damage by rescaling the f. So I make the new f, the old f of c over bt. If I do that, then all of these things cancel out and I go back to the same thing. So clearly, scaling up by b here and scaling up by c here should be one of the possible transformations. But there's more. There's one more scaling thing that I can do. And I'll show you exactly what it is. So first, there's a direction in space in which the choice probability will be the biggest. Maybe it's 1, maybe it's just 0.93, but there's one direction that will be the biggest. Suppose for a second that we didn't have a generalized Euclidean distance. Sorry, let me go back. Suppose that we didn't have a generalized Euclidean distance. That means that I will use just the regular Euclidean distance. Okay, so all my balls for my inner product norm will be just the standard circles. Then the direction in which the maximum probability will happen will be the direction of the utility. But because I have a generalized distance, okay, when I'm looking here at what is the direction of maximum choice probability, I'm not going to have just the utility. I'm going to have the utility multiplied by the inverse of my Gaussian, of my variance-covariance matrix. Okay, so this is very easy to check. There's one unique direction of maximum choice probability, which is exactly given by this. So if you have the sigma and the u, you know what is your direction in which 2 objects are going to be maximum against each other. That direction turns out to be always orthogonal to the indifference plane in any representation. You can have multiple representations, but you look at all the objects that are indifferent to each other. There are 50-50 choices. And those, according to the inner product of this norm, they're always going to be orthogonal to that maximum choice probability direction. Okay? So I can take the space of objects, and once I have a representation, I can separate it into the dimension of maximum choice probability and the dimension orthogonal to that. Okay, so 2 dimensions. It turns out that you can scale those 2 dimensions separately. Instead of just rescaling the entire norm by a constant c, you can rescale the direction of maximum choice probability, the norm in that direction only, by a constant d, and the remaining of the norm by a constant c. Okay, so you can always talk about the distance between 2 objects as having 2 orthogonal components, and you can transform the representation and get an equivalent representation by scaling each one of those 2 components separately. So the full permitted transformations to talk about uniqueness requires 3 scaling factors, b, c, and d. So you rescale the utility by a b, you take the distance between x and y and you split it into the orthogonal components, and then you rescale one by c and the other one by d. And then it turns out we found out exactly what is the nonlinear transformation you need to do to the f to undo the damage and go back to normal. And so these are possible, and the proposition says that these are the only possible ones. So how do I get uniqueness? If I'm going to estimate, just make sure that you normalize your b, your c, and your d, and then you know that everything will be point identified. The f, the u, and the sigma are point identified once you take care of these 3 scaling. So it's like von Neumann Morgenstern. You can add, you can always do a linear transformation, and you have to normalize if you're going to estimate it. Here, this is exactly what you need to normalize if you're going to estimate a model in this family. Okay? So uniqueness, that tells us the sense in which I can uniquely measure the differentiation between the products. Now let's go to, this is the formal statement. Let's go to the characterization. So here are the 4 axioms. The behavior can be generated by the formula. If and only if, the theorem says that it's if and only if I satisfy these 4 things. First is continuity. Okay, so you can see from the formula that this is going to be continuous outside of the diagonal. Okay, that one's easy. Then I have linearity, and you've seen this before. This is exactly the Gould-Pessendorfer 2006 linearity. So these 2 are sort of already familiar in the literature. The ones that I want you to pay attention to and discuss more carefully are the 2 new ones. Okay, we have 2 more axioms. One is I'm going to call independence, although I'm still not sure that's the best name. So if you have a better name for me, please let me know. And the other one will be moderate transitivity. So let's go to independence. I'm going to read the statement. If x and y are 50-50 with each other, and they both beat z, so x over z is larger than 1/2, y over z is also larger than 1/2, but x actually beats z by more than y, and you give me any number between 1/2 and 1, the mixture between x and y that has a lot of x and a little bit of y has to beat z more than the mixture that has a lot of y and a little bit of x. Remember that alpha is larger than 1/2. So here I'm doing the 2 symmetric mixtures between x and y. Here I'm putting a lot of x and a little bit of y. Here I'm putting a lot of y and a little bit of x. And if x was the most powerful against z, when you mix a lot of x, you still have to get the most powerful combination against z. Okay. So I can illustrate this real quick. I think it's good to see a picture. Here's the independence. So let's say that I have a trip to Paris right here and a trip to Rome right here, okay, to do a homage to Tversky. And this is a trip to London. And London is worse than both, okay? Paris and Rome are 50-50 with each other. They have the same level of utility, but London has a lower level of utility. However, here's my generalized Euclidean distance. And if you look at the balls, you see that this circle shows how far Paris is from London in our level of differentiation. And so Paris is closer to London in this differentiation metric than Rome. Rome is in some big circle over here, okay? So Paris, because the denominator is smaller, beats London more than Rome beats London. Now, one consequence of having an inner product norm is that when I do the 2 combinations, this is the 50-50 between Paris and Rome. Here I have a lot of Paris and a little bit of Rome, and here I have the opposite, a lot of Rome and a little bit of Paris. Every time you have ellipsoids, you're going to have that this combination is going to be also closer to London than this combination, just like in this picture. Okay? And so this is a consequence of assuming that the norm comes from an inner product. Let me show you how it can fail. If I don't have an inner product norm, now my balls in the norm can have other shapes. They don't have to be ellipsoids. And so here, there's another norm telling me, if I use another norm that doesn't come from an inner product, I have exactly the same situation, but notice that this square here is closer, so that this combination is closer to London than this combination. There will be a bigger square here. And so if you have weirdly shaped balls, this axiom could fail. Okay, so this is the axiom that is gonna pin down the fact that the norm is inner product. How many minutes do I have? 15? Perfect. Okay, so that's independence. I think that's not too hard to swallow. Here's the last one. Let's go to the last axiom. Moderate transitivity. And yes, there's some finesse here on what I'm going to say, but it's the following. If more than 50% of your population chooses X over Y, ranks X over Y, and more than 50% of your population ranks Y over Z, moderate transitivity requires that X over Z is strictly larger than the minimum between those two. So if this is, let's say, 60%, and this is, let's say, 80%, then X over Z has to be at least 60%. Okay. So it has to be strictly larger, or you could have equality here, but the only case in which I'm going to allow you to have equality here is when they're 60%, 60%, and 60%. Okay? That's moderate transitivity. In the paper, we actually started the paper writing a lot about moderate transitivity. It's like a little discussion of the axiom at the end. That's part of the evolution. I think like we were in love with moderate transitivity, but the world apparently is not in love with moderate transitivity. But what you should know about this axiom has a long history also in the literature. When you teach a Mascolel class, there's only one way to do transitivity in deterministic ways. But when we're talking about market shares, there's at least 3 ways. So I could say that you're weakly transitive if when A beats B and B beats C, you require that A also beats C by more than 50%. Here's the moderate transitivity. It's related to the minimum between those two numbers. And there's something called strong transitivity that will be even more, require even more of the behavior. That if this is 60% and this is 80%, A over C has to be at least 80%. Okay? That turns out to be too restrictive. This is the problem with logit. Logit is strongly transitive. And this is the reason that logit is too not flexible enough to accommodate the data we're interested in. When there's differentiation, you impose this, and you're in trouble. Okay? So naturally, we're using for our categorization a moderate level of transitivity. You will see a lot talk about the weak and the strong in the literature. We're sort of showing that moderate transitivity can be a good compromise between having predictive power and having explanatory power. Yeah. Say it again.
Why is 1/2? I'm a bit slow because I'm tired, but why is 1/2 important here? So, majority voting, or you have to establish how do you define a notion of transitivity? Like in Mascolel would be if A is always chosen over B, and B is always chosen over C or preferred, then A has to be chosen over C. Because rho B over A is the complement, because it's a complementary. Yes. Okay, no, that's why I was missing.
Okay, so that's the last axiom, and so the statement of the main theorem is that those are all testable implications, but those are all the testable implications. Every time you fail to reject those, you are going to be able to write the model like this formula. Okay, I have 10 minutes left. I'm going to tell you...
9. I have one question.
Yes.
So, going back to the name, so I thought that linearity is always capture the independence axiom in some sense, right? So what you show us is kind of, I just want to think again about this, what you call independence. It's some sort of monotonicity there, right? What is the role, for example, of the rho xy equal to half in the premise?
Yes, so think you're onto something. You could think, let's go back there. Real quick. Where's my row? Here. Yes. So one way to think about this is that you have some sort of independence, but only with respect to mixing with the middle point. So I'm taking Paris and Rome, Paris is beating London more than Rome. And if I mix both of them by the same amount with the middle point between them, I obtain this, and I need the inequality to be preserved. So that could be another intuition to try to find some sort of name. Okay, I'm happy to talk more about this after we're done, but let me show you what we can do with this theorem, okay? So we're going to do 3 things. And I'm just going to glance over. First, we can take this result to see what can we help the random coefficients literature in I/O. Okay, so if you look at Hausmann and Wise, BLP, NIVO, there's many estimation exercises for demand systems in which they say that utility is linear, but the vector of coefficients is a random variable. And one popular choice is to make them normally distributed. Okay? So this is clearly one particular example of our formula, because if you look at the probability that in your population the utility is maximized by choosing X, that's exactly the CDF of the Gaussian distribution multiplied, here you have the average beta on the top as a linear utility, and the variance covariance matrix of the Gaussian distribution is exactly the one that gives you the inner product. So this is a specific case of the formula that we're studying today, but you're insisting that you want a Gaussian distribution for the F. Okay. So what do we learn? One, our identification results tell us something that wasn't in the literature, that you can identify these parameters just from binary data. Okay. 2, we develop an extension in which we add a price dimension. We take it to multinomial choice now. Okay, take this normal to multinomial choice, because in I/O they actually don't have just duopolies, they do multiple choices. We extend it to have a price dimension, treat price as observable, which they usually do. And we make the assumption that the price enters only the numerator. It doesn't change the level of differentiation. And then we show that you have one of these models and it satisfies our axioms, then the distribution of the betas has to be elliptical. And elliptical is just a nice generalization of the Gaussian. Okay, so this is one specific example. If you want to get all the possible Fs, how much you can mess with it, go to the family of elliptical distributions, and that's exactly what you get. This result translates really nicely to the random expected utility over lotteries of Kulpe-Sendorfer. So instead of having just all of our n, we're looking just at the simplex of lotteries. But all of our results are very easy to apply corollaries, including the a characterization. So first we show, let me show something here. It's a question, right? What's the connection? Is every random expected utility model can be written in our formula? Or does any binary choice from our formula can be extended to a multinomial one that is random expected utility? The answer is no and no. They're not nested. So we show examples of how you could have one of ours that is not a random expected utility, and one of theirs that is not a binary one. But then we characterize the intersection between the two. The multinomial choices that are at the same time a random expected utility, so you can think of a population of von Neumann-Morgenstern agents. It's just like the Bernoulli index is heterogeneous in the population. And that at the same time can be written in the binary comparisons with our formula, so we can talk about the differentiation between the objects. Okay. And the characterization we get is that you get the GP axioms. So we already had, in the GP axioms, we had continuity and linearity and some other things there in the paper. And then our transitivity and our independence, and you get exactly the intersection between them. Moreover, if you allow me to charge people for the lotteries, if I add the price dimension, you not only have choices over lotteries, okay, so yes, here's 30% of winning the banana and 70% of winning the mango, but now you have a dimension in which you can charge for them. Then you get again the uniqueness. The only distributions that you can use to generate our formula come from the elliptical. So this is saying that we pin down what is exactly the shape of the heterogeneity of that Bernoulli index in the expected utility formula. Again, generalization of the Gaussian. And finally, do I have 5? Okay. So I want to tell you what happens when we go to a finite abstract set of options, which is a problem in which mathematical psychologists have worked for years. De Breu and others have worked on problems leading to what I'm about to do. And so what we do is, instead of having all of our n, now we just have n options, and we don't know where they live anymore. Okay, it's just a finite abstract space. So we observe all the binary choices from all the pairs from some abstract set of options. So let's look at our axioms real quick. What do you think is going to survive? So where are my axioms? Axioms. Here we go. Continuity is meaningless here. So continuity goes down the drain immediately. You're not going to test continuity with a finite number of options. Linearity is also meaningless here. We're not in Rn anymore. It's a finite number of objects. We're going to throw away linearity. Independence also is going to have, doesn't have a byte. But moderate transitivity does have byte. With a finite number of objects, you could reject moderate transitivity. Okay? So in our last application, we go to this abstract finite setup, and we solve the problem that Half proposed in the 70s. And we have the following characterization. Where is it? Where's my theorem? You have Half's formula, just with an abstract distance, if and only if you satisfy the moderate transitivity axiom. Okay, so we get a full characterization of when is it that you can talk, even when you only have finite number of comparisons, when is it that you can represent them with some notion of distance between them. It's not going to be an inner product norm. It's just going to be an abstract distance. And the answer is if and only if you satisfy this one testable implication. This is really nice because you can go to data, and this is very easy to test. I had a bunch of examples to show you. But instead of that, I'm going to tell you how this third application to a finite abstract space completes some sort of research program that is very long. So you now have a complete staircase of formulas where our formula is here, okay? This is the Half formula with the utility and the distance and the F, okay? That's called a moderate utility model. And in one of our applications, we show that this is equivalent to being moderately transitive. And now we have the complete staircase in order of generality. You can impose something stronger, which is strong transitivity plus, and it was known by Tversky and Russo. There was a characterization of a model they called simple scalability, where you don't have a distance and you just have an F that depends on the utility of X and the utility of Y. If you go even stronger and you impose something called acyclicity, you have a result by Fudenberg and co-authors that characterizes Fechnerian utility. Okay, so it's exactly the same formula but without the distance. And if you go even more specific and you impose something called the product rule, you get exactly the logit formula. Okay, so we can go all the way down from our formula all the way to logit. But we also got, as a bonus, a last proposition where we say, hey, what if this distance doesn't really need to be a metric? You do just a semi-metric, and we relax the triangle inequality. Well, then it's going to be very easy to plug any denominator you need here. The only consequence that is going to be left is that you're still going to be weakly transitive. So weak transitivity is equivalent to this that we call a weak utility model, where you throw away the distance. What does that tell us? The gap in behavior between moderate transitive and weakly transitive is equivalent on this side to the triangle inequality property of our differentiation metric. Okay? And so that's our third application, and I'm going to stop here and take any questions. Thank you very much. I'm going to show you some data then. There's no questions, I'll show you data. So you take this to data, you take any data set, and the moderate transitivity is super easy to test. Oh my God, I have so many slides. I was going to do it on the iPad, and so I had to produce the PDF, and I think a lot of stuff made it. Let's find my data sets. You see the proof? Okay. You see that picture? So just a curiosity. If you're interested in random choice, if you're interested in random choice, of course you're Oops, 1965. So this problem, that staircase that I just showed, it's something that we've been working on for a long time. So yeah, a long time ago, already the moderate transitivity, strong transitivity, and weak transitivity postulates have been proposed. They just haven't been characterized yet. So that figure with the staircase that I showed you is the modern version where this program here is completed. So that's a neat observation for you to compare. Anything else? Where am I? Here's the data. So that data, remember that the two triangles were easier to compare? So this one is chosen over that one 85% of the time, and this one is chosen over that one 50% of the time. To be strongly transitive, like logit, you would need the first one versus the third one to be at least 85, larger than the maximum. Too restrictive. But this one is still larger than the minimum, so it satisfies moderate transitivity. Okay. And directly testable. You just eyeball it. You don't have to run a regression. You can just use the moderate transitivity as a sort of non-parametric test for what's going on. Here's another one. Here's my favorite data set in the world, the frogs, that I use in another paper. B is chosen over A 63% of the time. A is chosen over C 84% of the time. If you want it to be strongly transitive, you would need B over C to be at least 84. But it's not. It fails strong transitivity, but it's still moderate to transitive. And then this is asking, this is screaming, please fit a model with an F, a U, and a sigma, and tell me what is the differentiation between A, B, and C, and what was the utility. That's what I did with a specific parametric form in a previous paper. All right. That's it. Thank you.
Okay, welcome back. Our next speaker is Pietro Ortoleva from Princeton.
Hello. Hi. Thank you for, well, let me thank the organizer. This was fun, super nice, awesome, everything. View, food, everything. And talks. So today I want to talk about a paper that it's part of a long series of papers that I started working on when I was in grad school with this chap, Mark Dean. And then we kept on working on these sort of related topics, and then a bunch of people joined along the way, Colin Kammerer, Jonathan Chapman, and Eric Snowberg. And it's a sequence of projects in which what we try to do is understand relation, in the sense empirical relations between behaviors. And in this specific project, what we try to study is the relation between fairly basic notions in behavioral economics, which are the willingness to accept, the willingness to pay, and loss aversion. So let me try to explain. All right, so the basic idea and the starting point is related to what David was talking about this morning, and is the relationship between the willingness to pay, accept, and willingness to pay. So just to recap what David was talking about this morning, suppose that I have an object, a wonderful pointer. It's actually a nicer pointer, I know. So this wonderful pointer, you may be interested in computing what is your willingness to pay. You don't have it. I show it to you and say, hey guys, how much would you pay for this? All right, I record it. In a separate group of people, I give them a pointer. I say, hey, it's yours to keep. But hold on, before you go home, could you sell it back? How much money would you want to sell it back to me? And I'm going to call it the willingness to accept. Now, according to standard theory, bearing income effects, which we know don't matter, so trust me on this, they should be one and the same, right? Because that should be the value of the object. But of course, as you probably know, Nobel Prize were awarded for the observation that they're not the same. And in fact, the willingness to accept is bigger than the willingness to pay, which is called, again, the endowment effect. And this is kind of a big deal because it means that we don't have a unique notion of value that we use when we make purchases or sales. Right? It doesn't mean, the fundamental idea of, 19th century economics is that we are human machines, we attribute value, we operate on value, right? That human machine notion doesn't work, at least in this evidence, because we don't buy and sell just based on that value. All right, so big deal. Now the beauty of this is that when people discovered this, they also had the story ready. And the story is the prospect theory story. The story is, you know why I have a higher willingness to accept than a willingness to pay? Because I am loss averse. The intuition is that losing is painful. Or, to cite Kahneman-Tversky, losses loom larger than gains. Now, if I think about selling as foregoing an object, as losing an object, this loss is painful, and I don't want to incur it. And therefore, to be compensated to sell an object, I want more money than I'd be willing to pay if I didn't have that object. And that's the fundamental explanation of the endowment effect in the literature. This is the leading explanation. To the point that, somewhat annoyingly, the literature sometimes misuses the word loss aversion to denote the endowment effect, even though these are separate notions. Instead, loss aversion as a notion has a history of its own. It was introduced by Kahneman-Tversky in the uber-famous prospect theory paper, and has to do with an overweighted losses in mixed gambles, or essentially a loss of risk aversion around zero. Now, while I was speaking, Christoph was shaking his head. Now I'm curious to see. You had, oh, okay, sorry. I thought I made a wrong historical citation. Christoph knows history better than I do, so I thought, all right. Okay, good. Another observation before we move forward. So this is the leading story. But even with this story, you may agree with me that the WTA and WTP should be related with each other, right? So sure, they might not be the same. But somebody who's willing to pay a lot probably also wants a lot to buy, and vice versa. All right. What I'm going to do today is to present an empirical paper in which I'm going to present the outcome of 3 incentivized surveys on 4,000 participants in a representative sample. So this is a very large-scale study. In fact, these are 3 large-scale studies, fairly well paid, a bunch of people. And in these surveys, we measure the WTA and the WTP for lottery tickets. I'll explain why lottery tickets is essential for whatever I'm going to say later. We're going to measure loss aversion, and we're going to measure loss aversion in a bunch of ways. And we're going to measure a bunch of other stuff that I will reveal as we go along to keep you interested. Moreover, I'm going to do some stuff. We're going to measure each of the things a bunch of times because one of my co-authors is a very good econometrician, and so he gave us sophisticated ways to measure, to use measurement error. And so, you know, I'm going to add some bells and whistles. We're going to create a panel data, so we're going to measure these things over time. We're going to test for stability. So as we go along, I'll give you some features about this. But the key thing we're going to derive from here is that I'm going to use this data to document 3 facts. Fact number 1, the endowment effect and loss aversion are independent. So the key feature is this. Prospect theory says people have the endowment effect because they are loss averse. Our data says no. There is no empirical relation between loss aversion and endowment effect. These 2 things do not relate with each other. So the loss aversion explanation of the endowment effect is really not supported. 2, the WTA and the WTP are actually independent. This is going to sound funny. How can they be independent? I'll try to tell you that it's not funny. But they're independent traits, even though we still get the endowment effect. That is, WTA is on average higher than WTP, but they are not correlated traits. This despite the fact that, just 1 second. Oh, yeah. Let me just throw the perfect. Now, you may look at this and say, all right, but maybe this is all noise. And the answer is no. Because what I'm going to show you is that the WTA and WTP are not related with each other, but they are related very strongly with a lot of other stuff. And also they're stable over time. So we have panel data, so we can test stability over time. So we have stable, these things are stable, they're just not related with each other. So what I'm trying to tell you here is the following, that there is a lot of structure. It's not that this stuff moves randomly. If the world was random, it would be a very sad world for economists because there would be no models to write, and as a theorist, I would be very, unhappy. But luckily for us, the model is not random. There is a ton of structure, but unfortunately, this structure, or actually, fortunately for young people, this structure is not the one we thought we had. So we have more theories to write. Yay! Okay, Christoph. Very good. So I'm going to show you this. No. So I'm not going to claim that in general WTA and WTP are not related. My wife is allergic to fish. She's going to have a very low WTA and WTP for sushi. I'm not, and I love it. I'm going to have a very high one. And of course, these things are going to be correlated. But so I'm not arguing they're completely independent, but I'm going to argue that in the world of lotteries, they're independent, that this is going to be important for point 3. For point 1 is also going to be important that I use lotteries because I need to make sure I'm evaluating everything on money. I'll elaborate on this in a moment.
So about fact number 1, so you are rejecting the prospect theory with that? Really?
I'm just saying, or at the very least, I'm saying, look, prospect theory says that one is explained by the other, and they're not related empirically. So, insofar as I can test it, it's really rejected.
Okay.
Okay, so let's see. A couple of questions before I move forward. How can this be new? Right? Prospect theory, Nobel Prizes galore. How can we, nobody tested this thing. I don't know, but nobody did. It turns out that if the only papers about the relationship between the endowment effect and loss aversions, well, one was written by me and Mark. And another one is a working paper that I think recently got published, but you know, it does things in a very different way. So for some reason, people never bothered to test the relationship between the endowment effect and loss aversion. I don't know why, but people never bothered. We did, and it turns out that, in fact, if you look at these two papers, there is a relationship which is fairly mild. And this is very different data. It's computed in the lab in a very different way. So, you know, as we go along, if you have time, I'll try to explain why we get different stuff. Also, you may also wonder, didn't people ever test the relationship between WTA and WTP? This also sounds not a crazy thing, no? You get the data, just plot this thing out. Well, it's subtle. People compare the averages. They looked at whether this one was bigger than the other one. To test the correlation, you need to have within subject, right? You need to have both per subject. Most experiments don't. The experiments that do never bothered. We bothered. So we looked at the old data, and insofar as we tried, for the majority of experiments, they're also unrelated. Then you have some that are very negative related, some that are very positive, but you know, like we're talking about old experiments with like 7 subjects, this kind of thing, so I don't know what to make of this. But on average in the data, especially if you pull all the data together, they are unrelated. So I don't think it's a special thing of our data set, it's just that people never bothered. All right. Good. If everybody's with me, let me give you a theoretical primer as to why prospect theory is predicting that they are one and the same. So, as you remember, and I'm really echoing and building on what David said earlier, prospect theory says that utility varies in relation to a reference point, which is fixed. But in relation to this reference point, losses loom larger than gains according to our parameter lambda. So a typical functional form, this is a special case, but a very common special case, is that the utility for gains is a concave function, the utility for losses is the reflection, but it's not exactly the reflection, it's a reflection weighted by a parameter lambda, which is called loss aversion. Now, how do you get the endowment effect out of this? Well, if you encode the act of selling as a loss, now loss aversion generates an endowment effect. Why? Because when I own this pointer and I sell it, it's as if I'm losing it, then I don't want to lose it, so I don't want to sell it. You got to compensate me for this utility of losing. Now here is a little bit more subtle, because what I'm doing is that I'm buying and selling a lottery, and now there are many ways to do it. There are 2 big ways. One is the Kazuhiro way. Another one is what's called third-generation prospect theory. What I'm about to say doesn't matter. You can do it in either way. You know, now detail, and the literature is huge on these things, and people fought on a lot of details. Luckily for us, these details don't matter for what I'm about to say. In any of these formulations, the endowment effect should be related to loss aversion, and in any of these formulations, when there is no loss aversion, there should be no endowment effect, and essentially one is driving the other. And let me actually compute it, just for simplicity. I'm going to just do it in the simplest way with linear utility and loss aversion. Let me just do the algebra. Suppose I have a lottery which is half 10, half 0, and I have this simple utility. What's the willingness to pay for this lottery? Well, it's the amount such that you're indifferent between buying the lottery or not. What's the utility of buying the lottery? If you win, you get 10 minus the price. But if you don't win, you get just minus the price, which is a loss, which means that if you do the algebra, the willingness to pay is 10 divided by 1 plus lambda. Now, what's the willingness to accept? Here I'm using third-generation prospect theory. Again, trust me, it's the same with Kazuhiro. This is saying if I have a lottery and I sell it, then it's as if I'm issuing it. So if I have a lottery and I sell it for WTA, if the lottery paid 10, I get the WTA, but I lose 10. If the lottery pays 0, I get the WTA and lose nothing. So then this is the calculation, and this is a typo. There should be no lambda here. But then you do the algebra, and you get this, and then you see that the ratio is exactly equal to lambda. So you see that the endowment effect, which is typically encoded as the ratio, is just the loss aversion, and there is no endowment effect if there is no loss aversion. Now, this is super simple because I put no risk aversion. I just wanted to make it easy, but you get the gist. Yeah?
Sorry to bother again.
Bother. Let's keep it
So yeah, this makes sense, but when you say it doesn't matter what generation of prospect theory, but what the endowment is or what the reference point is does matter. Namely, that you need that is to be stable. So if I start asking questions and start thinking about selling, then already my reference point becomes the money I'm getting. But in another way I'm asking it, then it's about not having it.
No.
So there is some stability across
No.
these
Very
things.
good. Yes.
And so I thought that the Korsegravin story was, even though they pin it down with rational expectation, that if my mind just wanders around, then my endowment effect also wanders around. Because it's like mentally, this is a
mentally, I'm already thinking of selling.
Yeah,
Absolutely.
I know
All of this is absolutely true. But what I mean to say is that the specific form in which you encode this, the endowment, you don't have an endowment effect without loss aversion. And loss aversion, right? However you want to encode it.
Yeah, I'm saying, but it can reverse. Like what's selling and what's buying is a matter
or
of framing.
if I enter into the frame of selling a matter, absolutely. But here, my data is going to be really plain vanilla endowment effect kind of experiments. So fair, in fancier experiments, you have to worry. We are as plain vanilla as you can get. So, all right. With this primer, let me tell you our data. So our data is
Pietro, quick question. All this will be also if you use probability weighting, more the thing on probability weighting rather than the lambda?
I mean, if you do probability weighting, if you start making asymmetric probability weighting, then it really depends on how you encode it. Because now you start having 25 moving parts. But if you encode it in the natural way, then it would get exactly the same thing. So most people write the endowment effect Solaris exactly with the goal to say that if you have no loss aversion, you should have no endowment effect. Because people really, but I think it's a feature, not a bug. They claim, I know why we have the endowment effect. It's because we're loss averse. Right? So this is what they're trying to highlight with the theory. Okay, our data. These are 3 separate surveys run between 2015 and 2020 in various iterations, all run by YouGov. This is a representative sample of the US population. We have 4,000 people, and about 1,466 have been tested 6 months later. So we have a panel for a bunch, and I'm going to use this panel feature as we go along. As I said, we have representative samples. YouGov is considered widely to be the most representative of representative samples outside of governmental ones. And in my estimation, I'm going to use weights. If you know what these are, that's standard norm. If you don't, trust me, it doesn't matter. Also, everything I say doesn't depend on this. In this thing, we measure WTA and WTP, 4 lottery tickets for each subject. Everything is incentivized, so we pay. The order between the elicitation between WTA and WTP is randomized. The order doesn't matter. Trust me, we've been kosher. All of this, all the appropriate tests have been done. In fact, they are not run close to each other. These are fairly long surveys, and we always take care of having them appear far away from each other. Moreover, each of them is computed for 2 different lotteries. So each person gives us 2 WTAs and 2 WTPs. Okay, and I'm going to use this as we go along. The way we measure it is using a multiple price list. That is, I'm going to give you the option, and then I'm going to ask you a bunch of increasing values and ask you where you want to switch. We have a multiple price list with 4 single switching, through which subjects go through a very extensive training. We have a lot of comprehension tests and so on, so we are fairly confident in the quality of this data. All right, how do we measure loss aversion? Now this becomes subtle because there are a lot of ways of measuring loss aversions. And we try to err on the side of caution, and we measure them in 3 ways. First way, some of my co-authors' favorite way, they call it DOES. This is a sequence of binary choices that are designed to estimate a parametric model of loss aversion, and these are designed so that to maximize the Bayesian information in these estimates. You know, we can spend hours about that. They have a paper about that, which is great. You should read it. But the key point here is that we use a sequence of binary choices to estimate parameters. Another way, which is maybe my favorite way, is instead we're going to measure the certain equivalence of a lottery with only gains, lottery with only losses, and lottery with equal gains and losses. And if I look at the way risk attitudes operates here, as opposed to these two, this is a measure of loss aversion. And third, what I can do is that I can measure a lottery equivalent of 0, in which I have a lottery with using lotteries with gains and losses. These are all 3 methodologies that have been used. Again, not knowing which ones is better, we tried all 3. Okay. Now, before I move forward, you may ask, why are we doing the WTPA and WTP for lotteries? Why don't we do it for mugs? The famous example from Kahneman-Tversky is mugs. Mugs are awesome. They're great for teaching. Let's use that. Well, we couldn't. And we couldn't for essentially a few reasons. We picked lotteries for a few reasons. First one, traditional. The endowment effect for lotteries is one of the original examples of the endowment effect. So if you go back to, the original ones, it's about lotteries. So, and it's widely documented. A lot of people claim it's more robust than the one for mugs. So we did that. But there's a more important reason. Using lotteries is crucial to test the relation with loss aversion. Let me explain why. If you're careful and you look at prospect theory, especially the way prospect theory is used, prospect theory allows for the parameter of loss aversion to be dimension dependent. I may be very loss averse towards mugs and not at all loss averse towards money. I may be very loss averse towards, I don't know, my grandmother's recipes, which I'm very much loss averse about, but not particularly loss averse about whatever, disposable stuff. Now, instead, if I want to compare loss aversion, I want to test prospect theory, I want to make sure that I'm focusing on the same dimension. If I use loss aversion, if we measure loss aversion for monetary gambles, and therefore I should compute the endowment effect for monetary objects, therefore for monetary gambles as well. That's the only safe way of properly rejecting the prospect theory. Because otherwise you may say, oh, but you are using different dimensions, and I'm assuming I can allow for the loss aversion parameters to be different in the 2 dimensions. And there's a third reason, which is one of the reasons why the endowment effect for lotteries is very popular, which is that I can endow you with a lottery ticket without giving it to you physically. I cannot endow you with a lottery without giving you I cannot endow you with a mug without giving you the mug. But I can endow you with a ticket, which is an object that pays, and is an abstract object, so I can endow it to you in a remote setting. Christoph. Hold on.
Money itself has no hedonic, so one could argue against saying that. That one could say that this is all true and absolutely makes sense, but money per se is A, fungible, B, has no direct hedonic.
Sure, I mean, I would disagree.
So then I would say
sharply,
that, okay,
but
so
it's fine.
So basically the argument is that if something has no direct hedonic attributes, then you can't really link, based on the data, loss aversion to the endowment effect.
I don't understand why.
No, I mean, this goes back to the issue. No, but so I'm just trying to say that in this context, it seems that what's really at stake is whether we can talk about loss aversion on money.
But loss aversion was defined for money, right? I mean, if I look
at... No, the Mark story was, I mean, it's a translation between, I understand.
Well, whether I can talk about the endowment effect for lotteries, I can, and I do, and there is data that predates the mugs. and then loss aversion was defined on money. No, am I wrong here? If I'm missing something,
I will ask it later. But there's all this discussion about whether I'm endowed to the single dollar, $1 bill that I'm paying with, or am I endowed to a mug that I own, even though you have an identical mug, but it's my mug.
very good. But
So, yeah.
if that was true, I shouldn't observe an endowment effect for lottery tickets,
Correct.
which I do instead.
Okay.
So that's fair. I agree. So you would say maybe there's no endowment effect for lottery tickets, whatever can be. Good. Other observation, you may ask, why do we measure it twice? Because what we're going to do is that I'm going to talk about correlation using a technique that two of my co-authors on separate papers developed, and it's called ORIV, Obviously Related Instrumental Variables, which is a way to study correlation using instrumental variables that reduces measurement error. So if anything, you should treat whatever I show you as an overestimated correlation as opposed to underestimate. We're using fancy econometrics well beyond my head. I mean, let me be honest, I understand a quarter of this. But it's the appropriate method. Yeah, good. Yeah, but here's there's only one dimension, which is money. There's no mugs.
So then what was your argument about different lambdas in different dimensions?
Sorry. If we had the mugs, we would have to worry about how we do dimension by dimension lambda i's. But we don't have mugs. We only have one dimension, which is money, so we don't have to worry. Okay.
Sorry, I didn't understand.
No,
Good.
we were on the same page. Good. Okay. All right, so let me tell you the results. Before I tell you the results, basic facts. What the WTA? The WTA is 0.9 of the expected value of a lottery, relatively well-behaved stuff. Remember, I measured the WTA twice because I have two lottery tickets. Turns out they're fairly highly correlated. They shouldn't be perfectly correlated because these are not the same lottery ticket, but they're fairly highly correlated. WTPs are a little bit lower on average, still fairly reasonable, highly correlated too. About the endowment effect, depending on the data set, remember I have three separate surveys between 67 and 62% have one strictly higher than the other. Between 9 and 16 have them equal, the remainder have the opposite. Absolutely in line with typical surveys, especially with a little bit of noise. So, you know, we are absolutely in line. The average size of the endowment effect is 0.2% of the expected value of the lottery. Sorry, not 0.2%, it's 20% of the expected value of the lottery, so fairly high. Fairly standard numbers in line with lab data. In fact, we were surprised how much in line with lab data they are. Yeah.
I don't know this literature. How are the surveys implemented? You probably incentivize them more than just asking them what would you pay for this lottery.
So what we do is that we say,
do you sell them the lotteries?
yeah, so the way it works is this. Suppose I'm doing the WTP, okay? I say, hey, here's a lottery, okay? With probability half it pays $50, with probability half it pays 0. Now, what you're going to do is that I'm going to offer you a list of monetary amounts, and then you're going to tell me for each of these numbers whether you want the monetary amount or the lottery. So I'm going to start from 0, it's going to proceed to 50 in steps. So for 0, you probably prefer the lottery than 0. But for 50, you probably prefer 50 than the lottery. And then at some point, you're going to switch from one to the other. This procedure is called the multiple price list. And it's uber standard methodology. Then suppose you want to switch at, I don't know, at a certain line. At the end of the experiment, I'm going to randomly pick a line here, see what you chose, and if in that line you chose the money, I give you the money. If on that line you chose the lottery, I give you the lottery. And if I give you the lottery, what does it mean? That I'm going to play the lottery. I'm going to flip a coin, and then if... Does it make sense? So one of our goals here was to try to be the least innovative possible. So we really tried, I don't know if we succeeded not to be innovative, not, you know, to replicate the standard method, but we were really trying not to be creative. Okay. Fact 1. The endowment effect and loss aversion are unrelated. Let me illustrate. I like to show stuff with graphs. So the loss aversion, we measure it in 3 different ways, using this parametric estimation, using the 2 certainty equivalents, 3 certainty equivalents, or using just 1 lottery equivalent of 0 versus a lottery with gains and losses. So let me just explain the last one, which I think is what I'm about to show you. Suppose that I ask you, do you want 0, or do you want a lottery pays half 10, half x? Sorry, half minus 10, half hex. And I ask, what is the x that makes you indifferent? If x is equal to 10, it means that you're indifferent between 0 and half 10, half minus 10, which means that you're loss neutral. If x is bigger than 10, it means that you need a higher price to play this thing, which means that you're loss averse, and how much bigger than 10 this is a measure of loss aversion, which is a non-parametric measure, but very direct. This is actually my favorite measure. Another measure is that I can do other forms of certainty equivalence, but these are all...
Right. And it's different from risk aversion?
Very good. What's the difference?
Sounds like what they learned as risk aversion.
No, but it is. But this is... So mathematically speaking, loss aversion is risk aversion around 0. So a lot of people debate, but this is what it is. So it's not. Yeah. Yeah.
So relative to other findings, which one is, so is it true that the endowment effect you find is smaller than sort of an average endowment effect, but the loss aversion you found is not? Or
No.
it's not true?
In absolute numbers, it's not entirely obvious how to compute. The fraction of endowment effect we observe is fairly in line, and the amount, I think, is not that different from typical experiments with lotteries. It's very different from the old Muggs experiment.
Yeah, because lambda equal to 2, which is huge.
Yeah, but I think most people don't think that lambda is equal to 2 these days. In data that's really not supported. So, if you look at modern experiments, various ones, you don't go to 2. Okay. So let me illustrate the fact that unrelated with a graph. Here I'm plotting what I just told Helios. This is the lottery equivalent. What am I plotting? Oh yeah, this is the endowment effect. And this is the lottery equivalent, this 0 indifferent to half minus 10 half x. And here I'm plotting what are these numbers. And these are like, I'm cheating a little bit. These are not exactly 4,000 data points, because this we measured only for 2,000 people, and they're jiggled a little so that you can see them better. But as you can see, there's no relationship. And in fact, if you do a non-parametric estimation, really general, you see that this thing is flat. Prospect theory says it should be like this. It's really not like this. There's a lot of people at 0, so you might wonder about, no, this look more because of the jiggling. In fact, the mass is, the super big mass is here. So we have to redo this graph because we have to enlarge the circle. But yes. In fact, let me do slightly more careful econometrics. What I can do is that I can run regressions, and using my 3 different measures of loss aversion, and different measures of endowment effect. It could be the difference, the ratio, the square root of the ratio, which is what you get with some funky formulations. I can use loss aversion. I can also estimate a parameter of risk aversion. I can control for it. If you do some version of Kosegi-Rabin, you will get that the endowment effect should be exactly lambda to the power of 2 over alpha or 1 over alpha, depending on which version you use. We tried them all. We didn't know. We just, throw it. Stata does it for you. I mean, I do nothing. But my co-authors know how to use Stata that says how to do it. And look. No, not related. Never. Here, you may wonder, oh, how about, you eliminate, people that have too low numbers, too high numbers. No, it doesn't come up. We tried to massage the data. It doesn't pop up. So, it's not related. So the take-home message from the, yeah.
Just a quick thing.
Yeah.
Is there any separate measure of like attention in the survey, like how much attention you're paying, and see if you restrict to that sample of the correlation changes?
Very good. So I don't have the graphs here. So what happens is the following. So we have measures of IQ. So if you look, and this is something we discussed in the paper, if you look at the super top percentile of the group, so these are the top 5% of people, and you look at young people, this correlation comes back at barely significant. It is.
Or if you try to restrict to a sample that looks more like the lab samples of really smart kids in, in X.
So if you got normal lab sample, not top 5%, but you go like top 50% of IQ, then this is not there. And we have a lot of data here, so we can look at response time, we can rule out people with the shortest response time. We couldn't bring it back up. So
got it.
That's, that's why we were convinced. And notice that we're stuck in, we're learning multiple regressions. I'm not controlling for my, so, I'm stuck in the deck against me, right? Because because I'm running all of these regressions and I'm running all of these subsamples, something gotta become significant. We didn't get it, so it's also true that we have 4,000 people, so, it's also harder to get spurious significance. Okay. Good. So there's no support for the endowment effect in prospect theory because what we're claiming is that these are independent traits. The second observation is that WTA and WTP, in fact, are unrelated to each other. And this is the second bit. This is the graph of WTA and WTP in our data. As you can see, there's a bunch of WTA. Oh, I forgot. This is WTA. No, sorry. This is WTP and this is WTA. I forgot to add the names. As you can see, the bulk of people is over here. There's a lot of people around here, which is not surprising. But as you can see in the cloud, there is no relationship. According to standard theory, these two measures should be one and the same. This is Econ 101. They're not one and the same. According to, once you allow them to get different, you should start getting stuff in this quadrant, and indeed most stuff in this is in this quadrant. But I'm telling you is that they're unrelated. Again, you may follow up on what Leo was saying. Maybe they're more related if I start becoming pickier and pickier. Here we did a ton of subgroups. We could not get any subgroup in which they're correlated, except, again, top 5% of IQ, young people, college educated. That's what we got. Yeah, so this is actually, here what I'm doing is that I'm just chopping extreme values. This is, again, a non-parametric fit. It's really not there. And again, I can show it to you. This
Pietro,
is
so loss aversion will ask, prospect theory will predict that you will have a linear line above the 45 degree?
No, so prospect theory depends on how you encode it. It allows for different types of correlation, but to get that they are independent using prospect theory, you need that the parameter of risk aversion and the parameter of loss aversion are perfectly going against each other, compensating. So you can get it, but it becomes super funny.
No, that's not my question. The standard prospect theory.
Yeah.
What will be the line that will be predicted? What will be the shape?
No, if you allow for heterogeneity of both lambda and alpha, then it could be a cloud. It doesn't need to be. Yeah. It doesn't need to be the line.
Yes.
It could be a cloud. But the point is that for them to be independent, these two parameters must have a distribution in the population that exactly compensate each other, which is at the very least implausible. So first of all, it's ruling out some forms of prospect theory, and it's also very implausible for others. But potentially, sure. But we use the previous part to go against to test the loss aversion part of prospect theory. Now, and this is just to show that this thing that they're not related is for every study. If you look at averages, if you do ORIF correlation, while at the same time, the measures of WTA and WTP individually with each other, so not across, but within WTA and WTP, are strongly related. Okay, so now you may look at this and say, dude, fine, but let me give you an explanation of everything. What you get is crap. It's just a bunch of noise. You measure random numbers, and you're telling me the random numbers are not correlated, so what am I learning? Okay, now let me argue that these are not random numbers. Observation 1. We use an instrumental variable trick to reduce measurement error, so that's already taken care of some. But you may say, what is this trick? Who knows? I don't know. Let me give you easier explanations. Well, second observation, WTA, the different measures of WTAs are correlated with each other, and the different measures of WTPs are correlated with each other. You say, okay, yeah, but maybe too similar. Let me give you another argument. Remember here we have panel data for almost 1,500 people. These are measured 6 months apart. So what I can do is that I can test whether these measures are stable. Incidentally, that's a whole paper by itself. So we have a separate paper about this, because to our knowledge, there's no papers about this, about stability. Now let me give you as a benchmark what is a measure of stability out of 6 months. The ORIF correlation for basic risk aversion questions in 6-month period is 0.3. Okay, and this is the highest intertemporal correlation we have. Sorry, this is not the highest, it's one of the highest. The highest we have is actually the one for WTA. So WTA, our measure of WTA is correlated over time, 0.36. WTP is correlated over time, 0.35. The endowment effect is correlated over time, 0.3. What I'm saying is that our measures are, insofar as there is stability, as stable as anything in this data. They're just unrelated with each other. And also, if you're curious, you may say, but there's something special in your population. No. My co-authors have a separate paper, which is beautiful, in which we measure the stability of preferences for the entire Caltech student body. And they find that risk aversion is correlated out to 6 months, again, 0.35. So this seems to be a fairly reasonable benchmark for stability over time, and our measures hit. So you claim these are pretty stable stuff. But more importantly, what I want to show you is that WTA and WTP are actually related to other things. Now, what other things do we have? So we've seen that WTA and WTP are not related to each other. The endowment effect is not related to loss aversion. But you may ask, maybe they are related to other features of risk preferences, because, hold on, these are WTAs and WTPs of lottery tickets. So your risk aversion got to matter in some way. Well, what do we have? We have certain equivalent of a bunch of lotteries, gains, losses, mix. We have certain equivalents for earn. And then we have lottery equivalents of fixed amount of monies and other lotteries. And you may say, how do these compare? And let me show you this table. And I'm gonna go slowly here because there's something I want to highlight. So here, I've divided my measures in measures that are called fixed lotteries. These are my fixed lottery. These are fixed lottery objects. What does it mean? This is a multiple price list in which there is a lottery, and I'm looking for their certainty equivalence. And here I have objects in which I have a variable lottery. I have either a fixed amount of money or another lottery, and I vary the lottery in the multiple price list. So this is a lottery equivalent. These are certainty equivalent. This is WTA and this is WTP. And this is the table of ORIF correlations. And what do we see here? Look, WTA is really related to risk aversion about bets on an earn, 0.66. This is super strong relation. Remember, WTA is related with itself, 0.7. And this measure is related with itself. We have 2.7. They are related across 0.66. They're really the same thing. Is this surprising? Not really. This is WTA for a lottery ticket. You see, it's not all noise. But hold on. let's look at this guy. How does it relate with the WTP? Let's see. Oh, not at all. And indeed, WTA and WTP are not related. It looks like WTP is not related to risk aversion. How can it be? That sounds nuts. All right, let's move forward. We have another way of measuring risk aversion for gains, slightly different wording. We're really trying to cover our bases. Same. Mixed lotteries, this. Lotteries with only losses, still related, not very strong. But now we get into funky territory. How about I look at the lotteries with variable, in which I vary the lottery with a fixed amount of money? Now I'm measuring lottery equivalents. Oh, WTA unrelated. And with two lotteries related, but you know, much less strong. On the other hand, look at these variables. They're very strongly related with each other. Now look at WTP. Now this guy is related with the variable lottery types. In fact, if you take these measures and you run a principal component analysis, what do you get? Of course, you're going to get two components. One that is these fellas all together, and one that is these fellas all together. Principal components are just ways to summarize correlation tables, right? That's a natural summary. So what are we seeing here? That indeed WTAs and WTPs are related to risk preferences, but with different features of risk preferences. And that's because my earn measure and my fixed money measure are not related with each other, which is incidentally well known in psychology and forgotten in economics, that risk aversion really varies depending on how to measure it. Well, it turns out that WTA and WTP are related to different features of risk aversion. WTA with the certainty equivalent, WTP with the lottery equivalent. Why? Well, turns out, not very surprising. Why? Well, here's a story. Okay, no, let me just summarize so that we agree. WTA and WTP are not related to each other, but each of them is strongly related to a different aspect of risk aversion. So in general, risk preference have two clusters. One, certainty equivalence plus WTA. The other one is lottery equivalence plus WTP. The fact that there are two clusters, these two clusters, is not entirely surprising. The fact that WTA and WTP entered this way is new. And now let me try to convince you of why actually it's not crazy. And you can refer to a paper by Charlie Spranger in 2017, not 1917, in 2017, that made the following observations, which is not his observation, but he tested it empirically. If you look at multiple price lists, the fixed element in the price list may act as a reference point. So when you have a certainty equivalent, your sure amount, your sure lottery of which you're looking at computing the equivalent is your reference point. And that is just like, well, the lottery is a reference point, but then it's just like the WTA, where the lottery is a reference point. If I do a lottery equivalent, the fixed amount is the sure amount, which is acting as a reference point, but then it's just like the WTP, and indeed is related to the WTP. So in a way, this structure makes all the sense in the world. All right. So let's take stock and let's go back to theories. What did we find? We found that WTA and WTP are independent. They're unrelated to loss aversion, but related to different features of risk preferences. What theories are going to go? Standard Econ 101, gone and forgotten, in the sense that Standard Econ 101 says that they should be, WTA and WTP should be equal. I'm telling you, not only they're not equal, they're not even empirically correlated. Prospect theory, that was a good contender. Awesome idea. Here it doesn't work. Not saying it doesn't work in general, but with this data, no. Other models, well, the first one I'm going to put is our own, that one dude presented this morning. Told us today And that model can explain it. But of course, this is not the only model that can explain it. Models of incomplete preferences can explain this. Models of salience can explain this. So there are models that are compatible with this evidence. And I'm sure other smarter models, maybe one of you will write, will explain this evidence. But, you know, our point here is not really to tell you which is the new model. We do it in another paper. But our point here is to, you know, to sort of take stock and start ruling stuff out. So just to conclude, in this paper we run 3 large-scale incentivized surveys on representative samples, in part of which we have a panel. And we document that the endowment effect is not related to loss of Earth. The WTI and WTP here are not related. And that the data, though, has a ton of structure because WTI and WTP are related to different features of risk preferences. This has theoretical implications. First of all, prospect theory is not doing great here, but other models are actually compatible with this. And again, my view, I have a fairly precise view about this. I see, I'm in the minority of the profession here, but I see the interaction between theory and data as a dynamic. And so I think that sometimes, you know, data should test theory, but also provide data points that new theory should fit. And so what we're hoping to do here is to provide new data points that new theory should fit. And you know, hopefully it's going to be it will be replicated, and hopefully new theories will fit. And a few caveats, just to conclude. Again, I'm really not claiming that WTI and WTP are not related to each other, because in general, of course, they might be. I'm saying that in this world of lotteries, they're not. It would be nice to test this outside. We haven't done it. It would be great to test it for, I don't know, mugs, cars, sushis, all open for future research. Of course, each of the models I've added have further implications. These further implications we cannot test in our data sets, but it would be nice to test those and see whether any of those survive. And I think I'm out of time. Yeah? Good.
Alô, tá baixo, tá vendo?
related to political economy. So Helios.
Hello, everybody. Can you hear me? Thanks for sticking around for the last talk. I might be a little incoherent. I've just arrived from the States and came straight here. So this is joint with Ravi Sethi. And we're going to talk today about something else, something different, politics. For a start, though there will be some decision theory in there of sorts, but the whole thing about politics is that then we want to aggregate and see aggregate results of these decisions, which are electoral outcomes. And so things like elections that happen in Brazil, the Bolsonaro election, the Trump election, I live in the UK, so the Brexit vote, were surprising to many of us, and there's a sense in which many of us think they were wrong, in a sense that we didn't correctly make that decision. The of information missed something, as if a lot of people didn't vote correctly. And there's a big question about whether new media played a role in this. And there's been a lot of articles, even in Brazil, about the role of new media in influencing the way people voted and giving a lot of biased news one way or another. And so that's what we're going to try to talk about in a model and see how this new media could affect elections. In fact, there's a plethora of new media now. Once upon a time, in the UK, there used to be the BBC. At 8 o'clock, everybody watched the BBC, or Rai in my country in Italy, and the 8 o'clock news in the networks in the US. I'm sure you had the same thing in Brazil. But now, these traditional media remain, but there's a plethora of other media we can read, especially from the internet. And so this is just an illustration for the US of the plethora of media we have from the left and from the right. And so you can pick and choose here very much what you really like to follow and fine-tune, and you're not constrained to 8 o'clock news that are. So there's a plethora of new media. That's the first point. The second point, and this is more a US kind of point, but maybe it applies also to Brazil to some extent. There's a big asymmetry, and this is between left and right wing voters on the trust they put on media. So in America, one of the clearest differences on opposite sides of the aisle is that large portion of Democrats trust many more media, a large, great number of media. If you look at a picture like this, you see trust in media from the left and from the right. So the right is red and the left is blue. And you see, the trust really in the last 5 years expands here. And there's a big dichotomy between 68% of left-wing guys that trust in general media and 11% on the right that trust media. So there's a big distrust on one side of media. Okay, this is this part of the rhetoric of politicians that helps that. Trump helps that. I'm sure Bolsonaro promotes a lot of distrust of media, and I'm sure you're familiar with that. So that's the second point. And so we're going to try to build a model of thinking about these two things. One is a lot of media you can choose from, and distrust that is differential on either side for media. So think of it this way. Think of it, there's two types of information that everybody gets, just to simplify things. One is the outside world, okay? So you get media from maybe mainstream sources or official media. There is media that you are involuntarily exposed to, okay? The outside. And then there's media that you actually choose, okay? So I choose an American, I choose to read Fox News, and I like that, and that, forms my beliefs on stuff, but I'm also exposed to other media somewhat, which I may distrust to a large extent, but there's also the outside. So this is the whole model, if you want. There's my beliefs about who to vote for will be made of two things. One is the outside world news that somehow hits me, and I may not believe it or hit me more or less, and the media I select. Okay? Based on these two signals, I'll form my opinion and I will vote. And each one of us, depending on where we are, will be exposed more or less to the outside and choose a particular media that influences us. And based on these two pieces of information, we will vote. Okay? That's it. That's the whole model. And so the theoretical question is the following. Citizens on the left and on the right are exposed to, or trust, if you want, outside media very different. Okay? So left and right, maybe the right trusts much less the outside news than the left. Okay? You can think of it, the right, they live more in the country side, and the urban
the mainstream part is correct or objective in some well-defined sense?
Okay, very good question. I have different versions of what I mean by mainstream, but I would say they are unbiased. Okay? They may be correct, but on average, they are unbiased. But, yes. So, the media is not.
O microfone dele não é muito bom. Será que é porque ele está mantendo longe? É.
Tá aqui, ó. É porque é direcional. A gente pode até trocar, tentar falar com ele.
Helios, yes. Try to keep the mic like this. Or use another one.
It's not a good mic. Oh, wow, this is a much better mic. I'll keep it for. Wow, I feel a rock star now. So, okay, so here comes the decision theory part or behavioral assumption that is novel. Well, there's a few things that are novel. This is certainly a big part of it. So we assume political identity. This paper is called identity-based election, right? And we assume people feel that they are on the left or on the right. They are, because of their upbringing, their culture, their tradition, right-wing or left-wing. Okay? And so they will make the choice of in media, the one they want to, if they choose Fox News, for example, they will choose it because with this objective, so that whatever news they receive from that, they will update rationally, but they will choose the source with a certain bias so that as often as possible, they will keep believing they have their heart in the right place in terms of their political faith. So if I'm a Trump supporter or a Bolsonaro supporter, I will choose a certain media that would tell me as often as possible, convince me exposed, given the news that it gives me, that I am right to be a Trump supporter. By I am right, I mean I will update rationally all the news I receive. So there will be no cognitive bias here. Okay? And so I will choose a media that has a certain slant that makes sure that as often as possible I believe I made the right choice. Okay? Yes? What?
Is my mind also accounting for the fact that I'm selecting
Yes, yes. Your mind will know the bias, will know.
So I know that I'm getting a selected sample.
Yes, yes. And so you could think of it as two selves. I have a heart that is pro-Bolsonaro, and I believe he's right. And I will, every news I receive, I'll update correctly, but I might choose certain sources that are biased in a certain way. And I will know they're biased, but I will choose them so that as often as possible, I believe rationally that Bolsonaro is right. And so how does this, well, the premise of this comes from a lot of political science. My paper is based on this identity-based polarization book, which says these two sides, the hearts being Republican or Democrats, have become very tribal and very strong in America, and many countries even here have become very polarized and have become a major thing to identify with. Okay, so you don't identify in terms of race, ideology, in terms of, religion or sorts. You identify really as a Republican or a Democrat in the US very much, and maybe here too, you are pro or against Bolsonaro. It seems like these polarizations similar. And so the whole gist of this is that political affiliations determine what type of information you absorb, rather than the other way around. You know, the information you absorb makes you determine the affiliation. No? This is kind of this guided information. Okay, so there'll be different parts to this model coming to your question here. So the first part of the model, I'll talk about unbiased. The outside world is unbiased. So it will give you a news that is, unbiased, so it's just more or less noisy, okay? And then I will talk about a model where the outside news is biased. And this could be talking about the outside news as maybe another country like Russia or Hungary, or, where, the leader controls the mainstream media and the mainstream media sends a biased information, okay? And then I can talk about misspecified models in which maybe the people think that the mainstream media is biased, but it isn't biased. This is very true in America, for example. A lot of Trump supporters believe that the mainstream news is biased, but it isn't. So that entails another type of a cognitive problem because you're misunderstanding the actual process. Okay? All right. So, yes?
Here, why do you need to have in your model these outside media instead of having just like a lot of different menu of other medias? Like, what role does it play having this?
The outside media. Yeah. Right. So I just want to say, I want to capture the fact that there's media that you choose and you fully trust because that's what you choose to read. Okay. But you're also influenced by something outside, something that you don't choose, that you're exposed to, and that keeps reality in check, in a sense. And I want to capture the fact that some people really distrust anything that's from the outside. You really only believe your Fox News, and everything outside you don't trust at all. And maybe some others have more trust on the outside. That's what I want to, this asymmetry I was trying to capture on the trust of media, I put there first, belongs to the outside media. Right? I put that asymmetry in levels of trust, and that's what I want to capture. And that's the main asymmetry I want to see what happens in an election when there's one side that really is in its bubble and listens only to Fox News almost, and the other side that's more open. Yes? No, it's exogenous. It's exogenous. Okay, so the literature quickly is, the paper is very simple, and it touches upon some papers here that look at correlation neglects. There's some very quoted papers that are from very famous people here in the audience that talk about how people aggregate, what happens to elections if you aggregate information, getting two signals like I do, but not understanding that these signals are correlated. They come from the same source or from a similar source, and you update, so you have a cognitive problem because you don't update correctly, okay? And so they want to see how that cognitive problem comes out into wrong electoral outcomes, because it's correlation neglect, okay? Very important aspect there. In that sense, it's very similar because we also have two signals. We update, but our model, we update rationally, so you know the cognitive. You just choose the media in a certain way. The preferences we have are behavioral and similar to these models have utility beliefs. The most similar one is this Kozegi paper in which there's an agent, it's not about elections, he's choosing whether to do a high-skilled job or a low-skilled job, okay? And he has to acquire information about his type. Am I a high-skilled guy or a low-skilled guy? But he wants to think he's a high-skilled guy. He prefers to believe he's a high-skilled guy. And so he acquires information about his type, okay? But he acquires information sequentially, and if he gets a signal that tells him you're a high-skilled type, he's happy with that, and he chooses the high-skilled job. If the signal tells him you're a low-skilled guy, he keeps acquiring another signal and another signal, because maybe that signal tells him he's a high-skilled guy, and so then he switches. So there's a bias. So maybe this is similar to how we do empirical work, and don't find an asterisk, and we keep looking, right? But this, in the end, the guy updates rationally on all the signals he receives, but biases the search. Okay, so exposed, he'll update rationally, but he has, this sequentiality bias of the search. We don't do this sequential search. We choose, so the update will be rational in our model, just like in these models, but we will choose the media, the different plethora of media, in using Bayesian persuasion in a way that I'll explain, okay? And then it touches upon media models, but in these media models, media is strategic in our model. Media is just all out there. So the model is very simple, very, very simple. There's just two parties, right and left, two states, right and left, meaning one is correct, one's not, and if R is the state, the signals are going to come out of the R distribution. There's a common prior, which need not be common, it need not be uniform. Let's keep it like that for now, because that makes it perfectly symmetric, and I want to capture other asymmetries. And there's two types of citizens. My heart is right, my heart is left. Okay? And so just take the R citizen, it's a purely decision theoretic problem. There's no gain here, there's just aggregation. So the R guy is taken as an example, okay? And so he will choose the in media. What is in media? He's got all this plethora of media out there, okay? All that picture I show you with the bubbles. There's all these media out there you can choose, and you will choose one of them that best suits you to preserve your political identity. I'll explain what that means. But what is a media? A media in this model is just, say, a two-dimensional variable that tells you what the bias is. And the bias is a two-dimensional object. In this case, it tells you how often you say R, the signals R when the state is R, and how often you say left when the state is left. Okay? So there's a two-dimensional object there, and each media has a certain characteristic of how biased it is. So maybe Fox News tells you R always when the state is R, and then tells you also R when the state is L a lot of the time. And then maybe it tells you L when the state is L sometimes only. Okay? So this is one type of media. okay, which will be very slanted towards R. And you will update correctly based on it, because you'll know it is slanted, but this is just one type of media. And you can imagine another media that tells you, you know, sometimes R, and here sometimes left. There's all these combinations, and that kind of represents that bubble I showed you at the beginning, okay? So each media, you know that has a certain characteristics, because you know Fox News has this type of reporting, and I model it as a certain type of, you know, media bias. And so you can assume the media as a sender with commitment, if we want to use the Bayesian persuasion language, right? It's a sender with commitment. You know it follows that rule, okay? So that's the way I interpret the media. Okay, and then the outside news, as the question came, for now, I'll assume it to be perfectly symmetric. So everybody's also exposed to some outside news, mainstream news, whatever you want to call it, and but people, and so this is perfectly symmetric news, so in the state R, it says R and LL with the same probability, so it's symmetric, but one side will be more exposed or more trusting of it. And I'll model that as having a higher precision, TL, than the other side, okay? So I hear some news, or I follow some news from the outside, and so I'll update more based on that than the guys from the other side, because they are more in their bubble, they don't listen, they don't trust. Okay? So there's two signals. One I choose, once the media I choose with a certain bias that's endogenous, and I choose it subject to knowing that I'm exposed somewhat to the outside world, and knowing that I trust the outside world or I listen to it to a certain extent. And the extent is different from the two sides. Okay? Yeah.
Rockstar. Conditional on choosing the signal, am I now give them the same weight as the objective one or not? If I chose a signal, I give them the same weight as the objective one?
You will choose a signal structure, you'll give it the same weight. Yeah, there's just, that's right. So let me say this. So suppose you're an R citizen, okay? You know you're exposed, or you trust the outside news with weight TR. So you receive an outside signal with precision TR. You know that, conditional on the state. And you will choose your in media, Fox News or whatever, which is a certain type of biased, in a certain way, a certain style of biased second signal structure. You'll give it the same weight in this sense. I don't know if I'm, okay? And that's it. You'll just receive two signals from the in media, from the outside media. You'll know the signal structures. You'll update rationally. You'll have a posterior. And you'll maintain or switch your political faith based on that. Okay? And that's all. So you'll stay for Trump, or you'll stay, so suppose you get two negative signals, you probably switch against Trump. And you'll know this signal structure. One, this is exogenous, and this is the one you choose. Yes? Intensity in preferences or in information?
In preference.
Relative to what? I mean,
I like to be, right wing, left wing, or.
Yeah. So for now, yeah. So we don't have it originating that. We could, but we just say you're just right wing or left wing. Okay. We could add some independents that don't have that. Okay. Okay, so everybody then chooses its in media, knowing it's somewhat exposed to outside media, gets two signals, finds out the posterior is rational, you update, maintain or switch your faith, and then we'll assume, we can have other assumptions here though, that you vote where your posterior belief is. Okay, so if my belief is more pro-Trump, I'll vote for Trump. Even though I don't like maybe you know, if I'm switching, then I don't like it, but I will vote the other way. Okay, so here comes the main preference. So this is a pure faith preservation motive. So the utility is, so you'll choose your media structure so that after you are exposed to the outside world and the Fox News that you read, your chance that you believe Trump is correct, if you're a Trump guy, is at least a half. Okay? So you get a 1 if this happens and a 0 if not. So if you maintain your faith, you're happy. If they tell the media you read, after all, tells you the media is wrong, you're unhappy and you'll vote for the other side. Okay? This we can relax. You need to be 1-0, but there needs to be something going on at 1/2, a little jump or some slope or something. Okay? But the key thing is that why are you choosing to read what you read? Because you want to try to make sure, you know, be convinced that your guy is the right guy. This is not different from me supporting, I support Barcelona, and I like to watch it in the Catalan channel that reports things and makes me feel good about the team even if you lost. And, you know, reports things with a slant, and I'm happy that, and gives me maybe tells me some information and not some other. And so that's why we model why people read certain things. Right, yeah.
Oh, so what happens if my utility is just my posterior? 1 minus or plus posterior depending on my... So this is very discrete, it's very discontinuous.
Right, so there has to be some jump at 1/2 or some slope at 1/2.
So it's linear,
perfectly linear doesn't work. Okay, this is because we're using Bayesian persuasion. Essentially, there has to be some jump. We formulated this thing as a utility. Okay, the payoff comes from the preferences, but it could come from actions. You could say, I will get a utility of 1 if I vote for Trump. And I will vote for Trump if I believe it's more likely than not to be right. And I will vote for the other guy. And so that's predicated upon actions and not utility, and those are naturally discrete. Anyway, this is, okay. So this is the, that's it. Okay, these are the preferences. I explain you why people read what they want to read. They'll be exposed to the outside world, and all I'm going to do, if there's no question, just solve this and aggregate and see what happens. And I have 10 minutes. Okay, so that's just in time. Okay, so I will solve this now, and I say, okay, we start from a common prior, 1/2. Okay, we don't need to, just simpler, and it's 50-50. At 1/2, we're exposed to outside world with some news, with some noise, okay? It's how much we trust it. And so that means we will receive something that tells us Trump is better than 1/2 or worse than 1/2 after that signal. We'll be more positive or more negative after that outside news signal. And given this, knowing this possibility, that's how we will choose our inside news, Fox News signal. So I will explain the inside news signal now, and the same will be for everybody else. So I start from 1/2. If the outside news tells me good, I'm happy. I'm confirmed that Trump is good. If it tells you minus, I'm not happy, and so I'll try to get news that pushes me over the edge here. If I trust more outside news, the outside news will push me more positive or more negative, so I'll have to try to react differently from it. And so that's the main difference, right? Okay, so here, in this case, what you have is that if after the outside news is good, then I'm fine. It's when it's bad that I worry. And so if the outside news is bad, then I'll try to choose a signal that when it's good just pushes me here over the edge. And when it's bad, and to do this as often as possible, I'll have to combine it with a news that when it's bad, it's terrible. Okay, this is standard 101 Kamenic against Bayesian persuasion, if you heard of that model. Anyway, you try to target this and push you over the edge as often as possible here, and then you combine it with this T that pushes you down intensely but rarely. And so this is a media signal that's one-sided. It tells you Trump is good most of the time. But then you know it tells you Trump is good also when it's bad, so you don't update too much. But then when it tells you it's bad, it's terrible. So if Fox News tells you Trump is bad, it's as bad as it gets, right? So that's the combination. The other combination that's possible, though, is this one, which is when you have you're more exposed. And so here you'll get good news. You want to react to this guy and push it over the edge, but it's very costly to combine it with a terrible signal like before because you'll have to do it too often. Instead, you can exploit the fact that when you get good news from the outside, you will be way off, and so you can combine it with bad news. You'll have to have good and bad news from the inside, otherwise you don't update. It'll be good and bad, and the bad won't be too bad, but so it can still keep you on this side of the half when it happens that the good news from outside is there, okay? So this is like a hedging strategy, which is different. It's like more mixed in a sense. And this comes out if you do also the convex Hall arguments that are typical in this literature. And so essentially there's two qualitatively different signals. There's one side, a signal maybe Fox Newsy, that tell you, R when the state is R, but also R when the state is L, and so you don't update very much, but so favorable news are frequent, so there's diluted the baby one, but when they're negative, it's terrible. So very biased, one-sided. And there's more two-sided news that you could choose that are more mixed, that are more good and bad in either state, and they're less one-sided, okay? So these are two qualitatively different. Of course, there's all the quantitative differences too in there. Okay, so this is the main result here. So in these two slides. So first, this is the precision of the outside news. If you are perfectly exposed to outside news, then there's no persuasion you can get from the inside news because you're perfectly exposed, you have a perfectly informative signal, and so you'll be happy when the signal is positive, 1, you'll be unhappy when the signal is negative, 0. And so you'll be happy 50% of the time, and so there's no persuasion given that your priors are half. As T drops though, you'll be more and more persuaded. You'll be convinced that your guy is correct and vote for him more often than not, and it'll be more and more effective as this goes down. Okay? But here you see that the blue GB signal, the two-sided, is better for more exposed or more trusting people, and the red is more effective for people with less trust or less exposed or more closed up, more in the countryside. Okay? Okay, so this is the persuasion. Of course, if you're perfectly closed up, you will always be persuaded because you're essentially in a total bubble. And okay, so let me skip this. So this is the main slide here. So this is again that same line unconditionally. So it tells you how often you're happy because the media cocktail that you're exposed to, that you partly chose, preserved your political faith. But this is what happens in the two states. This is the average. In the good state, this is how often you'll be happy. In the bad state, this is how often you'll be happy. And here the same with the other good and bad state. Okay? So that's that. And now I want to say, okay, so now let's go back to the first slide. One side is very closed up, very distrusting of outside news. It'll be here. Okay, you'll choose red, and the other side is maybe average here, and you'll choose blue. Okay, but now suppose blue is the correct state, so no Trump or no Bolsonaro is the right state. That's where signals come from. Okay, so what will happen is that this guy will go here, will be persuaded this often, and this guy will go down here, right? But if you mix them, depending on the parameter values, you can get that this guy, even though he's in the bad state, the fact that he's closed up and he chose this Fox Newsy channel makes him persuaded more often, 96% of the time, than this guy that is correct but chose more an average signal, less biased, that on average works better than the other side, but then in this state works worse than this guy. So these guys here convince, our side convinced these guys 96% of the time, and the L citizens that are right only 94% of the time. So if you aggregate this situation here, what you obtain is that R wins all the time. When it's wrong, by a little bit. When it's right, by a large percentage. So regardless of the state, Bolsonaro wins, or Trump wins. And this is in which situation? In a situation in which these fans are pretty closed up, and the other fans on the other side are mildly trusting outside news as well. So first point is that there's a winning margin advantage for the closed side. Yes, okay, obvious. The other side, the other thing that's important is that this advantage can be enough to win symmetric elections all the time. And so L loses even when it's the correct party. So there is no information equivalence. So I cannot talk about welfare here, really, because the preferences are weird. Okay, so but I can talk about information aggregation because people are updating rationally their signals. They're perfectly updating their signal as known. Okay. If there's correlation between signals, I cannot say they win always, but I can say it wins most of the time, even if it's wrong. Okay, so if there was no outside news, so when there was only the BBC, and we had not all this choice to target media, we would have a perfectly symmetric outcome. Even if one side distrusts the BBC much more than the other, it doesn't matter. That aggregates into a perfectly symmetric situation. Some guys get more noisy signals, some guys get less noisy signals. There's no choice. They cannot fine-tune their media, and so correct outcome always perfectly symmetric. The whole point is that when you choose your media, you can choose it in such a way that even if you update rationally, the wrong guy wins. And a lot is determined by the fact that these guys choose blue, that it's better ex ante, rather than red, that is worse exposed. Okay? So, you know, if these guys were choosing media in a way to say, oh, we shouldn't choose blue, we should choose red, because, you know, those guys that are reading Fox News are very extreme, we should choose something more biased as a response, then that would work. That would work, that would defeat it. But I don't think that's what people do. We don't read the New York Times because we want to defeat them. It's just an individual pleasure that we have into reading, and in my model it is about us, you know, thinking that we're on the right side as often as possible. Okay, how much time do I have? It's almost over. 5? Okay. And so, but this looks like a very small region. So of all the region here, this is the trust of one side, this is the trust of the other side. Almost everywhere there is information aggregation. The region where there isn't is where one guy is very distrusting and the other guy is average. Okay, so this is the region when R always wins. The other regions are correct guy wins. Okay, you need one side very distrusting, very closed, and the other guy average. Okay, so if you move here, you will see if this is more trusting or less trusting, there's also a correct information aggregation, correct guy wins. Yes?
Could we interpret, maybe could we interpret that as like if this traditional media loses quality, such a thing that more likely to happen?
Yes, if traditional media or trust of the left drops or increases, then we could have information aggregation again, and maybe that's interest of politicians. Also, if these guys increase their trust, and so there's an incentive for these guys to be low if you're on the R side. And so that's obviously what Trump or Bolsonaro try to do, seed distrust of traditional media. Okay, so then we can have a lot of extensions, no? We can say, okay, if these guys do not understand correctly the signals, if this guy's getting the same signal with the same precision, but thinks it's more imprecise than it is, so distrusts incorrectly, doesn't matter, that doesn't change. If the average is not 50-50, it's even unfavorable to Trump, he can still win all the time, so it's not knife edge. Maybe the one I like best is, you know, we can have, I said we have the same priors, but we don't need to have the same priors, especially maybe I'm a Trump guy. I don't believe they're 50-50 to start, maybe he's 60% right, and the other side believes they are 60% right. Suppose you have that, then the result is emphasized. So the region where this reversion happens is much larger, because there's a lot of guys that are already convinced here, regardless what happens, and the other guys need more convincing, and so there's a much bigger region relative to here where R win always, so it becomes more pervasive, this failure of aggregation in the whole space. Okay? So anyway, I'm going to wrap up, and so all I want to say is that the different exposure of from outside media drives quantitatively and qualitatively different media that we pick and choose. But it's the qualitative difference in the media that we pick and choose that can drive on aggregate very skewed electoral outcomes, and you can have Bolsonaro winning and you wonder why. Well, that's a consequence of what type of media they picked, and given that the fact they're very exposed, combined with what media the other side picked. Yes? Yeah, so I'm just basing myself on the original graph on the trust of the left versus the trust of the right. That's very, on average, different, but then there could be fringes. But yeah, there's just two hearts, and assume one side is more distrusting, much more distrusting than the other. Okay. I can talk about propaganda, but there's the same model you can do in a totalitarian state where the media outside is propaganda, and people can be on the government side and also choose their media, or on the opposition and choose their media. And I show that you really need censorship there. So if you don't have censorship on top of propaganda, propaganda is easily defeated. And so you can see why a lot of these totalitarian governments like Putin or Orban don't want to have other media to choose from, because you can defeat very easily in this model the propaganda, okay? If you can choose your own media on top of it. Lastly, the last thing I'm going to say is that there's a model of misperceived propaganda. So suppose there isn't no propaganda, so the outside signal is symmetric, as before, but one side believes it's biased against them, right? Which is what we see a lot in me. So if you have that, so it's a misperceived model, people are cognitively impaired beyond having their heart in a certain place. This doesn't matter, you get the same type of graph. If the R believe the outside signal is just biased against them, it still works. The same flavor of the result where R always wins in this region remains. So the same kind of punchline is there. Okay? So very simple. Two information sorters. The outside we're all exposed to somewhat. We believe it or not. We believe it's biased, but it's not. The inside we can choose in partly to shield against this outside news if it happens to be unfavorable. Elections just aggregate information based on this decision theoretic thing in which we are choosing one media and we're updating rationally on two signals, and the goal is just to understand the difference on this differential distrust in the two sides. And the result is that the low trust on one side and average on the other combination generates this failure of aggregation where one side wins all the time, whether it's right or whether he or she is wrong. Thank you.
So for your result, you have to play with this this plenty of media, right? So you can choose, right? So there is no regulation in a way, right? So regulation on the type of, you know, suppose you think, I don't know how much you can incorporate that, fake news or some kind of warning about this. So do you have any idea what regulation this term could change things, or?
Yeah. So a lot of the results are based on the fact that there is this whole space of media we can choose from, which used to not to be there, right? And now we can really pick and choose the media with the bias we want and fine-tune it. I want to say this is not a model about fake news. I don't know how to think about fake news. People are just getting a signal that has noise. And maybe you know that it's biased more on one side than the other, but you're not fooled by it. You just update correctly and reverse engineer the bias it has. So there's no, it's not a model of fake news, right? And I'm thinking, but there is fake news in this world, and I'm thinking about how we could model it, or what it would be of fake news. Maybe it has something to do with misperceptions when we maybe misunderstand the structure of the signal and we update incorrectly. But I don't know, so this is, as it is, it's not really...
So some media is going to push you towards more the right state, and the other push you towards the wrong state. So it's the fake news could be something like related to that distance, right? How much you are using a media that is against the truth.
Yeah, but it could also be called, I don't know, precision. So I don't know. I don't know where the boundary goes from imprecise to fake. I don't know. Yeah.
From a political economy point of view, and I agree that your model doesn't get any normative consequences, except that sometimes it says that the right guys is never elected. Your model. So it could be that actually, coming back to my previous question, that it would be optimal to have actually on both sides extreme guys that are isolated.
Yeah. So if both sides are isolated, then at that point, the persuasion is better, and the two sides become symmetrically, essentially asymmetric. The whole point is that what that asymmetry can get you. That's the exercise, essentially. And if the asymmetry is big, one side's almost distrusting, and the other guy is average, that's when you get the thing. Yeah.
So I know that you said that like the utility is not very meaningful, so you can't do welfare comparisons. But looking from a social choice theory perspective, when you have these kind of preferences, do you know if there is some literature like what is the best way to aggregate them when you have preferences that are not like exogenous? They depend on what kind of media do you choose.
You should ask the decision theory experts in the room, which I'm not. I didn't want to go into that exercise of welfare because it takes some assumption on what. Well, I guess I could do it. I could say it would mean. Well, it would require more assumptions. Maybe I have a welfare effect based on who I believe is right, and then there's another welfare effect on who's actually elected, because that's also would affect my utility of sorts. So there'll be more assumptions I need to make. Whereas information aggregation is just simple. It's just people are receiving two signals, they're updating. All this wealth of information that's out there, is it giving me the correct outcome? That means the signals come from a state W, R, or WL. Do we match it or not? So it's just a simpler concept. But you can define welfare, but I feel I would need more structure and more assumptions.
Yeah. Also, you're opening a lot of doors to potentially funky things like that maybe we don't want to elect the best person because the right-wingers will be more disappointed. Then, you have to adapt reality. So, once you open the welfare door, if you use traditional econ tools, that's a dangerous door to use here. Right? So I think maybe safer to...
I'm happy to keep it closed, yeah. Especially in the...
One thing that I didn't understand it, if you consider the mainstream media neutral, it's neutral in your model?
In the main model, it is. Then there's the propaganda part, which assume it's biased because it represents an authoritarian state, official media.
If mainstream media is neutral, why people distrust on it?
Well, well, that opens a big door.
Because to me, your model is not realistic on this point, because if some people are really distrust on a neutral media, it is something wrong with your model.
Well, look, I mean
that you didn't talk to us, but you.
Okay. So this is an assumption that I have, and that's my premise. Okay, so that's my model. And now you say, is that a justified assumption? And I can tell you, well, look, there's this differential distrust here in the data. And now you ask me why. And I can tell you, look at this. For the US, this here, this is Trump. There was already an asymmetry, but Trump comes in, boom. You see here, this is Trump saying, to me, this is not about my models, just to answer your question. This is Trump saying, and he's been saying that explicitly, and maybe Bolsonaro's been saying the same. I'm not as knowledgeable as of Brazilian politics, but he's been sowing distrust of the media and generating this thing, which helped him in my model. That helps that their side is distrusting of the outside, because then they're more in the bubble and more persuadable by the source they do choose, Fox News, for example.
Can I criticize your paper?
Yeah.
You have two lines, very different. So the mainstream media are agreeing with that people in the above the midline. Eh? So we have people disagreeing. So the mainstream media that you assume neutral is not neutral, because a lot of people are agreeing with that and disagreeing with the let's say Trump supporters. So to me, just this graph is saying to me that the mainstream media is not neutral. Just seeing this figure,
It may be.
Maybe.
It may be.
Yes.
It may be. Or it may not.
So to me, why not to model just in the two different sides, because it looked like old wine in new bottles. What did you do? So why not just assume that mainstream media is not neutral, and assume that mainstream media is liberal side?
I have. Okay, so that's the propaganda part.
Okay.
Okay, so, but I call it propaganda, and I apply it to a non-liberal democracy. But maybe you're very welcome to say, no, that applies also to current liberal democracy.
Okay.
But, so yeah, so what that media, what you're saying is consistent with that. It could be.
I don't have a question, but I want to use this time because we are about to finish.
Yeah.
To thank the organizer and everybody for a fantastic conference.
Yeah, thank you very much.
Okay, so let's clap for the talk. And thank you everyone.
Berto.
Just wanted to make sure.
Thank you, guys. Good luck out there.
Outside.